From stardust, our sun was born. It ignited to create our planetary system, shaping the conditions that allowed life to emerge and thrive on Earth. But what is our sun made of? How does it affect the world around us? Join me on this video where we will be talking about an element that plays a crucial role in the formation of stars like our sun, and I'll show you how scientists figured out what stars are actually made of. Before there was a sun, there was a cloud. In fact, a giant cloud of gas and dust floating through space, just one among countless others. This cloud, however, was special, unbeknownst to the sun, Earth, and all of us humans watching this video right now. But for some reason, this particular cloud would eventually come to play a major role in the future of the cosmos. At least that is if you happen to be a fan of Earth or planets in general, because this particular cloud contained most of the material that would go on to form the sun and our entire solar system. But back then, about 4.6 billion years ago, the cloud wasn't doing anything too exciting, just floating around being mostly empty space with trace amounts of hydrogen, helium, and lithium, which had been produced during the Big Bang and were the first elements in the universe. Stars were beginning to form all over the place. Gravity caused the gas clouds to collapse in on themselves, increasing the density and temperature until nuclear fusion ignited in their cores. And it's here where our story begins, because the birth of the sun, as we know it, depends on these tiny particles called neutrinos. These almost weightless particles whiz around the universe at close to the speed of light. They pass through matter as easily as if it weren't there. They're produced by the sun in such vast numbers that over a second, trillions upon trillions of them pass through your body without leaving a trace. We can't see them, we can't feel them, yet these tiny particles played a critical role in making the sun the life-giving star that we know. Neutrinos are created when protons and neutrons combine to form the nucleus of an atom, such as those found in the sun's core. This transformation releases energy in the form of neutrinos, and the newly formed nucleus recoils. But without the neutrinos to conserve momentum, this recoil turns into heat. Heat that creates pockets of high-pressure plasma. These hot plasma pockets expand outwards, creating a shock wave that blasts through the sun's interior. And the neutrinos stream freely out into interstellar space. For a long time, astronomers thought that all neutrinos were exactly alike, but today we know better. They come in different flavors, so to speak. There are electron neutrinos, muon neutrinos, and tau neutrinos. And each of these can change from one type to another via a process known as neutrino oscillation. In other words, a tau neutrino can transform itself into an electron neutrino or vice versa. The sun produces all three, but the vast majority are electron neutrinos, because they come from the nuclear reactions happening in the sun's core. And this is where things get interesting. Scientists have figured out that the sun has a deficit of electron neutrinos, meaning fewer electron neutrinos are coming from the sun than expected. So where are they going? Some scientists thought that maybe the electron neutrinos were changing into other types of neutrinos, thus disappearing from the electron neutrino category, and this seemed to solve the problem. But then other experiments showed that the muon and tau neutrinos did not increase accordingly. It was only in 2001 that scientists working on the Sudbury Neutrino Observatory in Canada finally figured out what was going on. The electron neutrinos produced by the sun were indeed transforming into other types of neutrinos, but not the ones scientists were expecting. Instead, it was turning into a neutral, electrically uncharged version of itself, one that scientists call a sterile neutrino. The sterile neutrino doesn't interact with other particles like regular neutrinos do. It's almost entirely elusive to detection, which makes it an ideal dark matter candidate. But its very elusiveness also means that scientists have yet to confirm its existence with absolute certainty. This all may seem like obscure science news from the early 2000s. But figuring out what's going on with neutrinos told us something incredible about the sun, you see. The sun's core is under tremendous pressure, which makes it possible for regular old hydrogen atoms to smash into each other and fuse together to form helium. That's where the sun gets most of its energy. However, this fusion process also uses up energy as well. If the neutrinos escaping the sun's core told us that the sun was losing more energy than it should, it could mean only one thing. The sun was made of something else besides hydrogen. Scientists could now say with confidence that the sun was mostly hydrogen with a bit of helium and trace amounts of heavier elements. With a newfound understanding of the Sun, scientists were able to fine-tune models of stellar evolution. Models that helped them answer some long-standing questions about the cosmos. Like, why did the Sun and other stars shine in the first place? Thanks to the efforts of the Homestake experiment, the Irvine neutrino experiment, the Super Kamiokande experiment, and the Sudbury Neutrino Observatory, scientists were able to figure out that the reason stars shine is because of a simple nuclear reaction, one that fuses hydrogen into helium and releases huge amounts of energy in the process. This discovery led to something of a scientific revolution. It showed that the elements that exist in the universe are forged in the hearts of stars. Not only does this explain why stars shine, but it also explains why they have the chemical makeup they do. Stars produce elements by smashing lighter nuclei together until they reach iron. After that, no additional nuclear fusion releases energy. The end result is a spectacular supernova explosion that scatters the heavier elements across the galaxy for other stars to use as building blocks. And so we got everything we need to form new stars, planets, and, yes, even life. Wow. All of this from a once simple cloud of gas and dust. This stellar nursery was mostly hydrogen, just like the Sun is today. But there was also enough helium and lithium for nuclear fusion to start. Now, not all stars are the same, but it's believed that most stars begin their lives this way. As gravity pulls the cloud of gas and dust together, it heats up the center until the temperature reaches about 10 million degrees Celsius. Then nuclear fusion kicks in, and the star becomes what astronomers call a main sequence star. That's when the star enters its longest-lasting phase, which for the Sun began around 4 billion years ago, and will continue for another 5 billion or so. The Sun is now shining brightly, giving off light and heat, and forming a solar wind that blows outward at 180 kilometers per second. Within the next few million years, a disk of hot gas will begin swirling around the young Sun. Leftover bits of dust and rock will clump together in orbits around the star. Eventually, these clumps will grow large enough to become planets. The inner 4 rocky planets will form quickly, but the outer planets will take millions of years to assemble. Meanwhile, the Sun will continue to shine steadily. It's providing the energy that drives the climate and weather patterns on the young Earth. Now, despite being mostly hydrogen, the Sun is not a perfect sphere. It bulges at the equator and rotates faster there, too. Because of this bulge, the Sun is actually wider at the equator than it is tall from pole to pole. What's more, the Sun has powerful electric currents flowing beneath its surface, creating magnetic fields that extend all the way to Earth. These magnetic fields store energy and channel plasma from the Sun to our planet, causing auroras at the poles. The Sun's magnetic field also creates sunspots, regions of intense magnetic fields and relatively low temperatures. When the Sun's magnetic field lines converge at a sunspot, they can remain in place for a long time. This allows energy to build up, which occasionally gets released in a massive burst of radiation called a solar flare. Solar flares can disrupt communications and electrical systems on Earth and pose risks to astronauts in orbit. But for the most part, the Sun is a pretty stable star. Its mass is great enough to keep it stable for billions of years. In fact, the Sun won't start to run out of fuel for another 5 billion years. At that point, it will expand into a red giant, engulfing the inner planets before it collapses into a white dwarf. But for now, the Sun is happily powering life on Earth. Without it, our planet would be a frozen, lifeless rock. With it, we can enjoy the warmth of summer days and the glow of a campfire on a winter night. And that's just 2 of the many reasons we should be grateful for our life-giving star. So what do you love about our Sun? Let us know in the comments section below. And while you're down there, don't forget to subscribe for more videos like this one. Thanks for watching, and I'll see you next time.